Okay, so we are on this section in your notes, velocity time graphs, acceleration time graphs, and here are some notes for area under a VT graph. It's just going to be shapes that you're familiar with. So rectangles and maybe some triangles, and that's it. Just as a review, what is the horizontal component of this rectangle for units? Time. And vertically you have good velocity. And then just like on my formula, what is v times t? Distance or displacement. Good. So that's how you calculate displacement from a VT graph. This is an absolute must. You need to know this. And it's been in the homework, so you should have already seen that. Now, finding acceleration from VT graphs, please highlight this word. So at the bottom of your page, you can put dt, vt, and at. We're looking at a VT graph. That's what we're looking at. If we want to go backwards to get displacement, we use area. And if we want to find rate of change of velocity, which is acceleration, we got to find slope. So area will take you back to displacement, and slope will take you forward to acceleration. If you look at the graph here on the right, it's linear. It's constant rate of change, which means every 2 seconds the velocity is going up the same amount. Every 1 second it looks like 5. Every 1 second it looks like 5. Every 1 second up 5. Okay? Or it looks like maybe it's 4 because of what work they've done here. Okay? So slope calculation, rise over run. Acceleration has this formula here. Change in velocity over change in time. This guy will be on your data sheet, which you can find in the back of your EPSB workbook. The blue one in front of you, you can flip that to the back and you will find this formula. Take a look at how delta V is expanded. It's V final minus V initial. So what was my final velocity? Take away what my initial velocity was in a certain amount of time. Okay? And just a word on units. It'll be meter per second, which is the acceleration unit, meter per second square. And we will do this in a lab. So just look at the connection between the VT graph and the AT graph. If this is constant rate of change, does it make sense that my AT graph is flat? Good. So here we have a VT graph. That's probably pretty standard for Physics 20. You have some changes in velocity over a certain amount of time. So let's just take a look at this graph and let's just talk about it. This first interval from 0 to 10, what's happening? The velocity is changing. In which direction? Positive. Good. We don't know what positive is. It could be north. It could be east. Why isn't this showing up? So much lag. Okay, there it is. So you have to find your reference. It's your 0. Up from that is positive. Down from that is negative. So in that first 10 seconds, are you accelerating? Yes. From 10 to 15, this interval here. Are you accelerating? Are you traveling? You're going at 60. So, and be careful, this is V versus T. So for 15 seconds here, you're traveling at a constant rate of 60 meters per second. Now from 15 to 40, what's happening? Your velocity is, yeah, so like what must have happened here magically? You've turned around? So here your velocity is 60 meters per second east, and now it's 40 meters per second per east. So what are you doing? 20 meters per second east. What are you doing? Slowing down. Here what's happened right here? You've stopped. And now you're traveling west, and you're actually speeding up. So here you're slowing down to a stop, and now you're speeding up in the other direction. Let me draw that on the whiteboard. Here's some object traveling to the right, and it's just traveling. I'm this almighty powerful God. I put my hand there. Okay? And it slows down. It slows down because I'm applying a force, right? It slows to a stop, and I'm still applying that force. What's going to happen? It's going to reverse direction eventually, right? All right. Let's answer some of these questions. During what time interval does the spaceship have positive velocity? Positive velocity, you are just looking for above x-axis. Above x-axis. And negative velocity, you're just looking for below x-axis. So your positive interval will be from 0 to 30, and your negative interval will be from 30 to 55, I think. At what time is the spaceship stationary? I think a lot of you might want to just jump to the flat part, but that's not the right spot. Where is the object stationary? Time equals 0, and the more important one is time equal 30. Good. Okay, thank you. 55, I think. So these spots, the velocity is, of course, 0 at those spots. When is it stationary? You would need v equal to 0. Determine the acceleration of the spaceship along each interval. First one, what's delta v? And delta t? You'd be like delta v, delta t, 60 meters per second in 10 seconds, 6 meter per second square. You guys okay with that? The next section is very straightforward because it's flat, so the acceleration there would just be 0, right there at that flat spot. Now for that big negative chunk, you're at 15, right? So what would be the delta t for that purple? 15 to 40. 25? Yeah. So you'd have 25 seconds in the denominator for your delta t. And then how much did you drop? And this is where it gets a little bit confusing because it's negatives. You're at 60, you get to 0, and then you get to negative 40. So what's the total change there? Good, you guys, 100. And positive or negative change? Negative change because it's dropping as time goes on to the right. So the acceleration there would be negative 4 meters per second squared. And this is what is tough for some students. You are having positive velocities, so you're traveling east here. You're traveling east, but you're accelerating in the opposite direction. If you're traveling this way but accelerating that way, you are slowing down. I'm traveling this way, but then I'm accelerating the other way, so I'm slowing down to a stop, and then I'm accelerating that way. That can be a little bit confusing at first. Okay, so you guys can do the last one on your own there. Just in the name of time. The fourth bullet, how far does the spaceship travel between 0 and 10? See how it says how far? So now we're looking for a displacement. So if you see that, you're thinking to yourself area. Thinking to yourself area. So from 0 to 10, here's 0, here's 10. You have to fill the space under the graph to the x-axis. What's this distance here in terms of time? 10. And then the velocity would be 60. So that's base times height, and then it's a triangle, so of course you have to divide by 2. You guys okay with the area of a triangle formula? Base times height divided by 2, 600 divided by 2. Okay, so 300 meters. And the distance, or its displacement, so what direction are you looking for? Positive. So whatever that let's just say positive is east. What about 10 to 15? What shape is 10 to 15? Rectangle. So you just need that small little rectangle right there. What's the height of that rectangle? And the time length is 5. 60 times 5. It's just a rectangle. So another 300 meters is traveled in that time frame. So the slide's a bit messy. You do have this practice in your workbook. So we have to be practicing that. It's in the homework yesterday. I want to see if there's one that's 30 to 55. 15 to 30. Yeah, the other ones are pretty straightforward. Let's do the very last bullet. What is the total displacement of the ship? This guy here, total displacement, you would have to take all this area, call that area 1, and all this area, call that area 2. Oh, backwards, my bad. This area, call that area 2. And what do you think you have to do with those two areas? Add them together, but one of them's below the x-axis. Yeah, so you'd have A1 plus a negative A2. Yeah, A1 minus A2. Above x-axis, that's positive displacement. Below x-axis, that's negative displacement. So it'd be like, you're traveling east and then you're traveling west, so the total displacement, they work against each other, right? But the second part of that, the total distance, you would just go A1 plus A2. It doesn't matter the sign. It doesn't matter the sign. Okay, this example 1.5, we'll switch gears, we'll go to the textbook. And if you don't have your textbook, it's all good. I'm just going to display it on the screen. So if you want to follow along in your textbook, it's page 27. And just to talk about how this class is structured, the textbook has lots of worked out solutions like this one here. Okay? And they're all pretty lengthy solutions, so sometimes it's worth just reading rather than actually doing it yourself. And then if you flip through the textbook, you'll find all these like questions on the right in these yellow boxes. That is where I pull lots of the quiz questions from. Like 90% of your quiz questions that you see are just right from your textbook. Okay, not all of them, but some of them. So I'll just borrow this guy's textbook. If you flip it open, you'll see these questions like this, these practice problems in these yellow boxes. That's where the quiz questions are coming from. Okay, it's so you could go ahead and work ahead in this textbook, and you would have all your textbook, all the quiz questions pre-done, if you wanted. Okay, so let's take a look at this board. From the table of values, position versus time, you see non-linear. If it's non-linear position time, non-linear, and jot this down on that page, this example 1.5 page in your notes, jot this down. Non-linear, and then put C textbook, non-linear displacement time. What does that tell you? Is the object accelerating or not? It is. So we call that non-uniform motion. So it must be accelerating. So the velocity must be changing. So what they do, and this is quite a difficult task actually by hand, is they go and find a whole bunch of instantaneous velocities. These are slopes of tangent lines. So they'll pick a point. So here at 2 seconds, they'll draw a tangent line and find delta d over delta t. They see it's 8.5. Okay. Then they pick another time here at 3 seconds, and they draw another slope of a tangent line and find it, and they see that it's 5.5 meters per second. So what can you tell about the speed? The speed is decreasing, so okay, it must have some sort of negative acceleration. And then what happens up at 5? The slope of the tangent line is flat, so it's stopped. Okay, and then here's the corresponding velocity time graph. Notice that the velocity time graph is linear. So here in Physics 20, this is all you'll ever, this is as difficult as it gets. A non-linear dt will get you a linear vt. And that vt, it might be positive slope, it might be negative slope, depending on the acceleration. So here you can see that the velocity is decreasing with respect to time. And that linear vt, you will have a constant at. Whether it's positive or negative, that's up to you to determine. But in Physics 20, you'll never have variable acceleration. In Physics 20 and Physics 30 in Alberta High School, you will always have constant acceleration. Variable acceleration is higher level, university stuff. And to find the acceleration, they will find the slope of this line, delta v over delta t, and you can see here the negative acceleration. All right. And you can see here that the textbook has some great reading to follow. Some of the stuff you could ignore, like biomechanics and the role of the crash test dummy. Like, I wouldn't read that. But this right here, negative acceleration does not necessarily mean slowing down. That's something I would read. So maybe this weekend you guys take home your textbook. All right, I want to show you some animations. Yeah. If the velocity, remember velocity is a vector, it has direction. Acceleration is also a vector, it has direction. If they have the same direction, they're going to speed up. Even if they're in the same direction, the opposite side, they will also speed up. So if you have negative acceleration, it doesn't necessarily mean you're slowing down. Because if you're traveling west and accelerating west, you are speeding up. Here you're traveling east and accelerating east, so you're speeding up. Now here when they're in opposite direction, here you're traveling east but accelerating west. Here you're traveling west but accelerating east. So these two you're slowing down. Now these animations will really show you how powerful this is. Watch this again, please. Do you guys remember the ticker tape from yesterday? See how they're closer together here and farther apart there? So it must be accelerating. The position time is non-linear, the velocity is linear, and the acceleration is constant. No, you can't draw it. You can only watch. There's 4 of them. So here you're traveling to the right, but accelerating to the left. Look at the non-linear. You could sketch them if you want, but non-linear. Do you want time to sketch them? All right. Do you want me to go back to the first one? Okay. So this is the first one. Please put that away. So hopefully the animated GIF helps you. Did you guys even hear what I said? The animated GIF? I'm just trying to mess with you guys. It's a GIF, right? GIF. So just as you're sketching this, if you look at the position time graph, what you can do to determine if it's speeding up or slowing down is you can look at the slopes of the tangent lines. You can sketch some tangent lines like I'm doing here on the whiteboard. And you can compare these slopes. And if they're becoming less steep, what could you say? Slowing down. Good. That would be, of course, for position time. Okay, and what do you notice about my slopes here? Are they up to the right or down to the right? They're up to the right. So the velocity, even though the velocity slope is down to the right, it's still positive. You see how it's above 0? That's important too. The velocity is positive, but the acceleration is negative. Okay. Can we do the next one? So this one will speed up because velocity and acceleration are in the same direction. And I'll just write actually right on here. Let's look at these slopes. What do you notice about those slopes? What do you notice about those slopes? They're getting more steep. So if the slopes of a DT graph are getting steeper, it's speeding up. But it's speeding up in the negative direction. And if you look at the ticker tape, it's accelerating left. It starts on the right and accelerates left. Can I go to the next one? Okay, this is the last one. You can with these new ones. So here, negative velocity but positive acceleration. So you're traveling left but accelerating right. And if you look at these slopes, steep, less steep, less steep, less steep. So you're becoming less steep. And if you look at the velocity graph, you're starting at a very low number, like minus 20, and getting higher. Okay? But that means you're going quite quickly in the opposite direction to going slower in the opposite direction. Positive acceleration. Can we move on? Just let me know. Is this good? All right, moving on. So I'm just going to give you the homework, and then we'll go back and finish that slide next day.